Okay, as we continue working with systems of equations, we've actually worked with solving them three different ways, and that was graphically, using substitution, and using elimination. And we do this practice so we can find out what is the best scenarios in which to use those, being able to make the determination, the best method, and working through that problem. And of course, because it's not going to necessarily be outlined in a real world scenario, but we want to be able to write and create these systems using real world situations or information, and then being able to then again solve them with the method. And when we're looking at these methods, things that you need to think about when you're looking at graphing, you would want to use the graphing method whenever you need to have some form of observable material. Substitution is something that you would use when you have a variable that is easily isolated. For example, in that example, if we have that as a system, I actually have x and y are both easily isolated there because their coefficients are 1. I just need to do a quick inverse operation, and I could move 2x over to this side, or in the other equation I could move 3y over to this side, and I've isolated both x and y to do substitution. And of course, elimination would be, I use that when I have opposite coefficients that I can combine to get 0. For example, 4x plus 3y equals 10 and 3x minus 3y equals 15. I hopefully can recognize that when I combine these systems using elimination, the positive 3y and the negative 3y become 0, and I've now eliminated a variable, allowing me to go ahead and move on and solve for x and then turn around and solve for y. So in this, as we use these considerations in these real-world scenarios, we're going to talk about finding the break-even point. Now, in the beginning, the break-even point, that's when my expenses are going to equal my my profits or my income, because I have spent enough money and I've earned enough money to break even. So that means I'm now back to where I was. And in doing that, what we want to do is we want to create an equation based on expenses and income. In this example, a puzzle expert wrote a new Sudoku puzzle book. His initial costs were $864. Binding and packaging each book cost 80 cents or $0.8, and the price of the book is $2. How many copies must be sold to break even? So in this case, how many copies of books, right? So that's going to be our variable. That's going to be our input. So let's go ahead and make books equal to x, because that's going to help us determine the income level or the cost of it. And so if our books equals x, we can think about expenses. What are our expenses? And our expenses are going to be the cost of printing the book, which is $0.8 times the cost of each book plus $864, because that's the initial startup cost. So that's how much it costs to print the book. Now, the income when you sell the book is going to be right here, $2 per book. So there we have it. We've created two equations, and in order to find the break-even point, as I said before, we need to make the expenses equal to the income. So in doing so, that would become 2x equals 0.8x plus 864. And what we have there is we have an equation which we can go ahead and isolate and solve for x, and that becomes, let's go ahead and just subtract both sides, and we get 1.2x is going to be equal to 864. And then we can go ahead and isolate the variable by dividing by the coefficient, divide both sides by the coefficient, and x is going to be 720. And what does that equal? That means in context, the price of the book is $2. How many copies must be sold to break even? That would be 720 books to break even. Okay, break even point. Now, looking at this next example, it says a fashion designer makes and sells hats. The material for each hat costs $5.50. The hat sells for $12.50. The designer spends $1,400 or $1,400 on advertising. And then how many hats must the designer sell to break even? So again, we want our expenses to equal our income. And in doing so, we recognize some of our expenses. Our expenses should be, advertising. We know that we're going to spend $1,400 in advertising. And then to make the hats, material for each hat costs this. So the material is going to cost us $5.50 per hat. That's what we're looking for. So let's go ahead and call our hats X. So that's our expenses. And then our income is going to be, well, it says right there that the hats sell for $12.50 each. So I should be getting $12.50 times each hat I sell. And now I can go ahead and solve and see what I need to earn here. So combining like terms, typically I'll always combine the variables to the right, but I'm going to go ahead or to the left, but I'm going to go ahead and combine them to the right just to keep from having a negative. So let's see here. Minus 550x on both sides. And that is going to give me $1,400 is going to be equal to 7x. Because 1250 minus 550 is going to give me 7. And then when I do my division, divide both sides by the coefficient, and it looks like x is going to be 200. So it looks like how many hats must the designer sell to break even? I believe 200 hats is the magic break-even point. Okay, as we continue on looking at the constraints and viable solutions, number two here, it's telling us the local zoo is filling 2 water tanks for the elephant exhibition. One water tank contains 50 gallons of water and is filled at a constant rate of 10 gallons per hour. And the second tank contains 290 gallons of water and is filled at a rate of 3 gallons per hour. When will the 2 tanks be the same amount? Okay, so the same amount. That means I'm thinking we're going to make them equal to each other. But what do we know? We know, depending on what variables we want to use, we could say that y is going to equal the gallons in the tank. And then x would be, I believe we're thinking about the number of hours filling, right? Because the number of hours that I fill a tank will depend on how much the tank weighs, or how many gallons are in it, sorry. So this is going to be my number of hours filling it. So tank 1, the first tank that we talk about, water tank, is going to be tank 1. It looks like it's going to be y, its total amount of gallons is going to be equal to 10 gallons per hour plus 50 gallons. And tank 2 is going to be equal to, y is going to be equal to 3 gallons per hour, and then plus 29. So when we go to make those equal to each other, we have our one tank, 10x plus 50, is equal to our other tank, because when they're going to have the same amount. There we go. And doing our inverse operations, I'm going to go ahead and minus 3x on both sides. And that's going to give me 7x plus 50 equals 29, and minus 50. Looks like 7x is going to be equal to negative 21, and oops. X is going to be equal to 3, negative 3. Now, -3, think about it. Can we have, it says, when will the tank have the same amount of water? -3 hours. We can't have a -3 hours. So what we're looking at here is it's never. -3 hours is not possible. It's not a probable answer. And we're going to have to just go ahead and write that one off and say, sorry, there's never going to be a way to get that. So looking at that, we're never going to be able to go back in time 3 hours. So it's not something we can achieve. The zoo and two other water tanks that are the zoo has two other water tanks that are leaking. One of those tanks contains 10 gallons of water and is leaking at a constant rate of 2 gallons per hour. When will the tanks have the same amount of water? Okay, so it helps when I use the entire question, and it says the second tank contains 6 gallons of water and is leaking at a constant rate of 4 gallons per hour. When will the tanks have the same amount? Of course, we're going to make them equal to each other, but let's think. Tank 1, Terminator 1, is going to have, one tank contains 10 gallons of water, so we're going to have 10 gallons of water and is leaking at a constant rate of 2 gallons per hour. So let me just reorder that a little bit. So we have 10 gallons of water, and it's going to be minus, because it's leaking, 2 gallons per hour, or 2x. And then T2, or tank 2, is going to be contain 6 gallons of water and is going to be leaking at a constant rate of 4 gallons per hour, x being the in the same as before, the hours of filling, or in this case, hours of leaking. So if I go ahead and make those things equal to each other, I should be able to solve, because all I have is an equation with variables on both sides. So go ahead and add 4x to both sides. And I'm going to have 2x, and I'm going to have 10, and that is going to be equal to 6, and then go ahead and subtract 10. I'm going to have 2x is equal to -4. Divide both sides by 2. X is going to be equal to -2. And again, the solution set of -2, that's not going to be a viable solution, because it's not possible to have time that is going to be -2 hours in this case. So they're never going to have the same amount of water in them. Again, I didn't solve for y, but I'm okay with knowing just this x portion of it. Okay, so getting into a current kind of question, and we're going to do upstream, downstream first. So as we are looking at the wind or current problems, it says you row upstream at a speed of 3 miles per hour. You travel the same distance downstream at a speed of 5 miles per hour. What would your rowing speed be and your speed of the current? So if we go ahead and assign some variables. So we know that we're going to be calculating the rowing speed of x, and then the water current, which is going to be y. And as I'm going upstream, the current is going to be working against me. So I'm going to be rowing, but I'm going to have to subtract the speed of the water of the current, because it's pushing against me. And that, we said, equals, I'm going to change that to a 2. 2 miles per hour. And this is going to be upstream. And then we're going to go downstream, and it says when we're reached downstream at a speed of 5 miles per hour. So that's going to be the speed I'm rowing, and the speed of the water is going to equal 5 miles per hour. So now I have a system, and I can go ahead and solve that. I have x minus y equals 2, or x plus y equals 5, and sure enough, we have the variables that we can cancel out using the elimination method. Cancel those out, and then rewrite as I add down. I'm going to have 2x is going to be equal to 7. Divide both sides by the coefficient, and x is going to be 7 over 2, or 3.5 hours. So I was able to find the, not hours, sorry, 3.5 miles per hour. And that is x, and we said x was the rowing speed, so that's how fast you're rowing, 3.5 miles per hour. In order to find your water current now, what we can do is we can just take that and plug it in right here into that equation. So we will go ahead and say that x plus y is going to be equal to 5, and I know that x is 3.5 plus y is equal to 5. Doing my inverse operations to isolate my variable. And then y is going to be equal to 1.5, or in this case 1.5 miles per hour. Okay, so that's how we do speed. And as we look at this next example, it's going to be air, but I think we can apply the same principles. So a traveler flies from North Carolina to Los Angeles with a ground speed of 495 miles per hour. At the same time, another traveler flies from Los Angeles to North Carolina at a ground speed of 550 miles per hour. What airspeed of each plane will be the same? Sorry, the airspeed of each plane will be the same. What is the airspeed and wind speed? Okay, so the airspeed of each plane will be the same. Okay. If they're flying, let's talk about the airspeed. We can call the airspeed possibly x. And then they give us this formula, right? My airspeed plus my wind speed is going to be my ground speed. So if my airspeed is x, let's go ahead and say that my wind speed, do I need a variable for that? Sure, y. And then my ground speed is going to be my output, or my number. So it looks like my airspeed is going to be, all right, let's go ahead and call airspeed A, our wind speed W. And then that we know for the first plane going from North Carolina to LA, our airspeed plus our wind speed is going to be equal to 495 miles per hour. Is going to be 550 miles per hour. And let's see, if we're looking at the US, something like that, right? And this, of course, is Mexico down there, North Carolina, somewhere over here, LA, somewhere over here. So as I travel from North Carolina to LA, well, I think what they want us to know here is that my jet stream, which way does my jet stream go? And I'm thinking my jet stream must travel in this direction. So as you follow your jet stream, you're going to have the airspeed plus your wind speed is going to be equal to your ground speed. And the ground speed is right there. But then when I turn around and I fly back across the country, it's going to be against me. So I'm going to have airspeed minus my wind speed, and that is going to equal 495. And I'm in a position that I can use elimination right here. So that will cancel out. Now I have 2a is equal to, and it looks like, well, 945